Okay, let's talk about on a few examples of Laplace transformation. So let's take a look on this first example. Let's consider function of time which is equal to exponential of t. So in here I indicated with e to represent exponential power of t. So let's take an example of a function ft where t is equal to 0 for negative t, and for 0 and positive t, ft will be equal to exponential of t. And then I want to transform this function of t to Laplace domain function. So in this case, I will use the formula that I presented in the first few slides to convert time domain function to Laplace domain function. So if you still remember how to convert time domain function to Laplace domain function, is by taking the integration of the function in time multiplied with exponential of minus st integrated over t, and then we evaluate it from negative infinite to positive infinite. But since the value of t is 0 for negative t, so I can just simply express this formula by just integrating from 0 to positive infinite for exponential t dft times the exponential of minus st, and then I will integrate it all over time by dt here. So I will integrate it. I just simply do mathematical manipulation. I will get this expression. I believe you can do it by yourself for this. This is just a simple integral operation. Then after I got this integration, I will be able to evaluate the result. I will evaluate it from 0 to positive infinite, and then I will end up into this expression. So 1 over s minus 1 is the Laplace transform of this exponential function in time. So 1 over s minus 1 is the Laplace transform of the exponential of t. If you look at the table again, if you refer to the table, on the 5th row of the second Laplace table, you will see the Laplace of exponential of minus at is equal to 1 over s plus a. If a is equal to negative 1, then this expression will be equal to exponential t, the one that we evaluated before. If a is equal to negative 1, so the Laplace counterpart of exponential of t will be equal to 1 over s minus 1, which is exactly the same as the one that we evaluated using the formula of the Laplace transformation. So in here, as I mentioned before, either way you can evaluate the Laplace transformation using the formula, the one that we discussed before, or you can also evaluate the transformation by using the Laplace table. Of course, to make our life easier, if I were you, I will use the Laplace table, which is much more simpler. But anyhow, this example just to show you, just to illustrate to you that either way, using the formula or the table, if you do it correctly, you will end up into the same results. One more thing that I want to highlight here, in this course, you will be introduced with a lot of new terminologies and a lot of new terms. And then I have one term to be introduced to you. The first term that I want to introduce to you is a pole. So what is a pole? If you revert to this Laplace function 1 over s minus 1, the one that we just evaluated before, which is basically this is the Laplace transform of exponential of t. So if you look at this function 1 over s minus 1, a pole is a value of s that will cause this function to be infinite or to be singular. So if I set s equal to 1, I will end up into 1 over 1 minus 1, or I will end up into 1 over 0, which is infinite. In that case, then 1 is the pole of this function, because 1 will turn this function to be infinite. So again, then pole is the value of s in which fs will become infinite. Okay, so this is the first term that you have to keep in mind. You will encounter this term many times in the future. Let's take a look on the second example here. So in the first example, we discussed about exponential function. Now let's take a look on the step function. You still remember step function? In one of the slides when we discuss about Laplace table, I mentioned that step function is a function where the value will be equal to 0 for negative t, and the value of this function will be equal to 1 for t equal to 0 or positive t, right? So in mathematical form, then step function, I can present it like this. The value of t is equal to 0 for negative t, and ft is equal to 1 for t greater than or equal to 0. And then let's try to transform this function to Laplace domain. So how to do that? In the first place, I will transform it using the formula by using this definition. Ft is this function, is the unit step function, so I will multiply it by exponential of minus st, and then I will integrate it by dt. I will evaluate it from negative infinite to positive infinite. But since the function of t is equal to 0 for negative t, I will just simply integrate it from 0 to positive infinite for 1 times exponential of minus st. You know how to solve this integration function? It's very simple, so I leave it to you. By using few mathematical manipulation, at the end you will end up into function of 1 over s. So this is 1 over s is a Laplace counterpart of the step function. Let's take a look on the Laplace table. So based on this calculation, we know that the Laplace domain of a step function is 1 over s. Let's take a look on the Laplace table. As you can see here on the second row, it is correct. The Laplace counterpart of the step function is indeed 1 over s. So you can see it here also. Using the table, you can find the Laplace counterpart relatively easy by just simply looking at the table. Let's take a look on the last example. Here I have an example of sinusoidal function. So I have a function here, ft, where ft is equal to 0 again for negative time, and then ft is equal to a sine omega t for t equal to 0 and greater than 0. If you still remember, in calculus it is mentioned that sine omega t can be expressed in this following exponential form. So you can also write sine omega t is equal to this form, equal to exponential of j omega t minus exponential of minus j omega t divided by 2j, where the j here denotes the complex number, the imaginary number. So by substituting sine omega t with this expression, and then using the definition of the Laplace transformation, I can transform the sinusoidal function in time to a Laplace domain. Okay, so I just substitute this form, the sinusoidal function form, to the ft on the definition of the Laplace transformation, and then by just doing some mathematical manipulation, I can solve this integration problem. At the end, again, I will leave it to you. I show how the working step in here. You can just follow these steps. At the end, you can find that the Laplace counterpart of the sine function in time domain will be equal to this one. The fs will be equal to a omega divided by s squared plus omega squared. It takes few steps to end up into this solution, but by just referring to the Laplace table, you can take a look here on the 11th row. You can find the Laplace counterpart of the sine function easily. In this case, I have sine omega t. Omega is the frequency. In the previous example, the frequency is expressed by omega. In this example, frequency is expressed by a here. So from this table, you can see that the Laplace counterpart of sine at is equal to a divided by s squared plus a squared. It also agrees with the Laplace counterpart that we evaluated using the definition of the Laplace transformation.